In this lesson, you will learn how to sequence the tasks in your application by using the state machine design pattern. The labels in this code example show that the programmer intends to execute these nodes sequentially from left to right. Which node do you think will execute first? By wiring the error wire, we've ensured that this acquire data sub VI will execute before this acquire data sub VI. However, these three nodes could all potentially execute first. The one-button dialog function does not have an error in input and error out output, so we cannot enforce its order of execution using an error wire. A sequence structure contains one or more subdiagrams, or frames. A sequence structure frame cannot begin execution until everything in the previous frame has completed execution. You can use a sequence structure to specify execution in sequential order. A sequence structure will always execute every frame and cannot skip a frame. These are caveats that come with using sequence structures. You cannot stop the execution partway through the sequence, and sequence structures will continue to execute all frames even if errors are detected. In this diagram, the one-button dialog function executes even if the acquired data sub-VI results in an error. Before clicking Next, how would you modify this code so that it does not execute the one-button dialog function if an error has previously occurred? Instead of using a sequence structure, you can put the one-button dialog function in case structures and wire the error wire to the selector input of the case structure. This has the added benefit of checking for errors. Now, if the acquired data sub-VI outputs an error, the case structure can decide not to execute the one-button dialog function in the error case. If you want to execute a sequence of code only if a certain condition is met, use state programming. State programming helps you solve issues that sequential programming cannot. For example, you can change the order of the sequence, repeat one item in the sequence more often than other items, execute items in the sequence only when certain conditions are met, and stop the program immediately instead of having to wait until the entire sequence finishes. Use a state transition diagram to plan the states of your program and transitions between states. A state transition diagram consists of states, which typically perform actions, and transitions, which define which state to move to next. In this state transition diagram, there are 5 states and transitions between the states. The first state to execute is the initialize state, which performs any necessary initialization actions. The initialize state always transitions to the acquire state, which acquires data. The acquire state always transitions to the analyze state, which analyzes data. The analyze state also includes transition logic, so if warning is equal to true, then the analyze state will transition to the log state, which will then transition to the check time state. If warning is equal to false, then the analyze state will transition straight to the check time state. The check time state also includes transition logic based on the values of time elapsed and stop. So the check time state can transition back to itself, transition to the acquire state, or transition to exiting the program. A state machine is a common design pattern that usually has an initialize state and a shutdown state, along with other states. State machines implement algorithms that can be explicitly described by a state transition diagram. If your application logic can be described by a state transition diagram, you should use the state machine design pattern to implement your application. Translating a state transition diagram into a LabVIEW diagram requires the infrastructure components shown here. Click on each component to learn more about it. Here we see a state transition diagram for an example application. Once you have defined your states, you must implement code to handle the transitions between states. Depending on the number of possible next states, there are several ways to control what state executes next. A single default transition, a select function transition, a case structure transition, or a transition array. Choose the method that best suits the logic of your state machine. For the single default transition, there is only one possible state that occurs next. Here we see a design that uses a default transition. Click on the case structure and the enum within the case structure to see how these correspond to the states and transitions on the state transition diagram. Here we see the select function used to transition between two states, depending on whether or not an error occurs in the acquire sub-VI. This method works well if there are only two possible next states. Click on the case structure or either enum within the case structure to see how these correspond to the states and transitions shown on the state transition diagram. If you need for your code to be able to transition to many different states, the recommended approach is to use a case structure transition. Here we see similar functionality to the select function transition, except now we are selecting the state to execute based on the output value of the analysis VI. As the application grows, you can add more transitions by adding more cases to the case structure. Click on the outer case structure and the enum within the inner case structure to see how these correspond to the states and transitions shown on the state transition diagram. Click on the case selector label of the inner case structure to switch cases. If you need more of the code to be visible than a case structure allows, you can create a transition array for all the transitions that can take place. In this example, the decision-making code provides the index that describes the next state. For example, if the code should progress to the error state next, the decision-making code outputs the number 1 to the index input of the index array function. This design makes the transition code scalable and easy to read. One disadvantage of this pattern is that for larger arrays, it can become complicated to maintain proper indexing and the array could occupy a significant amount of block diagram space. Click on the outer case structure or any of the enums within the case structure to see how these correspond to the states and transitions shown on the state transition diagram. This is the state transition diagram that describes the exercise. You will create an application that uses the state machine design pattern that will acquire a temperature measurement, analyze if the temperature measurement is in the expected range to determine if a warning occurred, log the data to file if a warning occurs, and check if 0.5 seconds has elapsed since the last acquisition. If the user has not clicked the stop button, the entire process repeats. In this exercise, you will implement this logic by using the state machine design pattern. Now let's take a look at the state machine code that implements this state transition diagram. On the left here, we see the initialization code where we initialize our DAC hardware as well as create our file. Next, let's take a look at our state machine infrastructure. So here we see we have the state machine data, and notice that in this cluster we have weather data consisting of current temperature, max temperature, minimum temperature, a warning status, and also warning text. Also notice that the first state that we will enter in the state machine is acquire. So let's take a look at the acquire state. In the acquire state, we have our acquisition code, and we also update our state machine data. So we update the current temperature here and update that in the shift register. If we take a look at the transition code, every time after acquire state, we will go to the analyze state. So now let's go to the analyze state. And in this state, we take a look at the state machine data again. We analyze it. We update the state machine data. And then we take a look at the warning status. And based on the warning status, this determines our next case to transition to. So we can either go to the log state if there is a warning, or we can go to the check time state if there is no warning. So let's pretend there's a warning, and let's go ahead and go to this log state. In the log state, we take our data and we log it to file. And then every time after that, we will always go to the check time state. So let's go to the check time state. And in this state, what happens is we just kind of wait. And the first thing we do is we take a look at if 0.5 seconds has elapsed since our acquisition state. So if the 0.5 seconds has not elapsed, then we will go right back into the check time state. If the 0.5 seconds has elapsed, then we will go back to the acquire state. The other thing that happens in this particular state is we monitor the value of the stop button. So if the stop button is ever true, then we will go ahead and exit the while loop and we'll be finished. The other thing to take a look at for this state machine is if an error occurs in any of these states, the error will also come into here and will cause us to exit the while loop. So if the stop button is pressed or if an error happens, then we will exit the while loop. And on this side, we will perform our shutdown code. So our shutdown code consists of closing the file, clearing the DAC task, and displaying errors if there is an error. So now I'm going to show you an example of a different way of implementing this state machine. So in this example, notice that we have our same weather data, but the beginning state now is initialize. So notice that the initialization code has been pulled into the state machine. So first we execute our initialize state, and we perform our initialization code. And after initialization, we always go to the acquire state. So once we go to the acquire state, we perform that code, and then we always go to the analyze state. And the analyze state performs its code, and then it can either go to log or check time. So let's go to the log state. And notice in the log state, we will perform our logging and then go to check time. So this looks pretty familiar to what we had before. One thing I wanted to point out that is a little bit different is the error handling. So notice that in this particular example, after every single state, we monitor the value of the stop button, and we also monitor whether any errors occurred. So if an error has occurred, or if the stop button is true, then what this code does is it'll go to this select node, and if that is the case, we will go to shutdown. So if we go to shutdown, inside the shutdown case, we close our file, we also clear our DAC task, and we also display errors if there is an error. And then we exit the VI. So this true is passed to our condition terminal, and we exit the while loop and exit the VI. You've completed this module. Here is a summary of what you've learned.